What eating? What two? What two?
Okay, let's stay on target and keep going through the material. Today is Monday's lecture for sometime in the future. I'm going to go ahead and apologize for myself in advance and say that there's something that's keeping me from having the quiz graded by now. I'm sure there's something that we can make up. I have to shampoo my dog or something. And so your quizzes will get graded hopefully in the near future. Actually, I probably will have them done within a couple days of having them in. So fingers crossed. By pre-recording, I should have a little extra time to do that in a timely fashion. Okay, let's get started for today. Last time we talked about common source amplifiers. Today we're going to shift into common drain and common gate amplifiers. So we have our little trifecta of different amplifiers here from the MOSFET. So let's discuss what we had last time. So for common source, why do we call it common source? Well, the source is what we tie to ground, right? And so when we draw our small signal model, we have this source as a common ground for our gate and our drain in the model. Similarly, when we talk about the common drain model, we're going to have our gate and our source up here, and they have the drain in common as a ground. And then finally we have our gate on the bottom, and make sure I get the orientation right. Yes, source and drain, they have the gate in common as a ground. So in the middle here, we have kind of an oversimplified version of this so that you can kind of follow along. But we're going to actually build from our standard bias circuit that you're used to seeing. And that provides a lot of insight into how we calculate the different parameters, the intrinsic properties of our amplifier. All right, so let's talk first about the common drain amplifier. So what we have here is our bias circuit in red. You'll notice that RD isn't present in this one. It can be there, but typically we don't have to necessarily worry about it. And if we're going to define it or design it in, we design it at the very end. So RD is usually defined at the end. And the way we get to the small signal model here is there's a little bit of a trick in here, okay? You'll notice that sorry, it's a little small. We'll keep it big. I just want to get some more space. You'll notice that the source and the drain have been switched, as promised. This is common drain. So what ends up happening here is we could draw our small signal model as follows. I'm just going to do it all in green. We've kind of done the outline thing before, so we won't do that again. VS goes to ground and RS. So that's our source resistor. And then we have R1 in parallel with R2 from the perspective of our AC. And notice here, these guys are both going to ground. These are going into the gate. I'm sorry, this should be R2, not RL. I don't know what I was thinking. All right, there we go. And then VGS goes between here and here. It's kind of weird to draw because in our standard way of drawing it, this would have to come, this arrow goes down, right? Because we're coming from the drain. So there would be our D here. And this D would be tied to ground. Here's a little RO. Here's our source. And this goes through RSS and our load, also to the ground. And then we take V out from here. I guess I should write this over on the side. V out. Okay, so that's effectively our small signal model, but this is really wonky to have to deal with. So what we're going to do is we redraw it with a different orientation on this stuff here so that it's easier to deal with. And you can kind of see if we flip this around and pop it in here for our MOSFET small signal, everything looks nice and clean, except our arrow direction has changed and our ID is flowing this way, as it should. And I think that's about it. Oh, another important part. VGS is now coming across this way, as opposed to what we had before, which was up and down. So we were able to exploit last time the fact that VI and VGS were basically the same thing. We can't do that here anymore. So we're going to have to be a little bit more careful about the assumptions that we make. There are some other things that we'll be able to exploit, though, as we move forward. Okay. So a couple other notes about this particular amplifier. It gives us a high output current. And that's really the biggest takeaway from this is we get an amplification on that current. We're actually going to get a little bit of attenuation. Some attenuation on the voltage. So we kind of gain some current at the expense of the voltage for our gain at any rate. So our voltage gain you're going to end up seeing is actually less than 1, which is fine if we use this as our first stage. So this is typically a first stage in a multi-amp setup. We also call this the isolation stage typically. So what this does for us is it provides a lot of the current for our other amplifiers that we're going to have down the line. Yeah, so expect to see a common drain at the beginning, and then typically followed by a common source or a common gate, depending on the application. All right, let's dig into some calculations now. We're going to go ahead and do the gain calculation first. We know that AVI, our voltage gain, is calculated as follows. We have V out over V in. And again, we're going to start by thinking about V out. And in this circumstance, we're actually going to, in the common drain, we're going to think about V out first, then think about VI, and then slap them together and see what we have left over. So we have V out is equal to ID RSS in parallel with RL. Notice here for the first time we actually care about this SS resistor. That sounds like a World War II like anti-aircraft or something. The SS resistor. It would obviously have to be like one of the Nazi ones, and Indiana Jones would blow it up. Anyway. Maybe it's a battleship. Who knows? Okay, so anyways, maybe I just need to watch Indiana Jones and just get it out of my system. Okay. So anyways, we have this SS resistor in here. The reason it's in here is because we don't have that capacitor bypass that we had last time. Remember, with the common source amplifier, we had a nice little bypass that took us to ground from our source. Not so here. We have to go through that resistor to get to ground, so it's going to play an important part in our calculation. Conversely, because our drain is going straight to ground, we don't have anything in here, so that's why we get this nice smooth line down here, but yeah, so RD and RSS have kind of swapped places with each other, moving between the common gate and common drain amplifier. And that's no surprise because we've effectively flipped on its head which part of the MOSFET we're using for our V out. So instead of having our V out come from up here, we're actually plugging in down here. So again, this should come as no surprise whatsoever, the fact that we have RSS now instead of RD. Okay, so getting back to this equation, we have V out is equal to ID times RSS in parallel with RL. Why is that? Well, the current that flows through from here is positive ID, right? It's not coming out, it's actually coming down. So it's not opposed to the ID. Comes down through here, gets split between those two, and then this is ground. So we have our current is well defined, our voltage is well defined, right? It's VO. I thought I got rid of U. Okay. And our resistance is well defined. So all we do now is just rewrite this expression, just like we did for the common source calculation. We can rewrite ID as GM VGS, but we also have that little RO, and it's going to be VO over RO for that, right? Because it's the same current that's going into here. Same current that's going into here is the same current that came out of here and here. So if we're use some arrows here, so this is coming out, this is coming out, this is going in, this is going in. Okay? So I have to split that current between these two, and that's how I express it here. All right. From here, oops, a little thick, RSS in parallel with RL. All right, from here it's just an algebra game. I'm not going to belabor it too much because we have a lot to do. So GM VGS, and it's going to end up being R out in parallel with RSS in parallel with RL. This should come as absolutely no surprise. We changed the sign, and we've replaced RD with RSS for our gain calculation. Now, we're not quite done yet. So this is just our V out calculation. Now we need to calculate V in. So this almost looks just like our gain from last time. Recall it was minus GM, and then the VGS top and bottom just canceled, right? And we had RO, RD, RL all in parallel, and that's all we were left with. So if VI was equal to VGS, then this would be great, but it's not. So we have to do a little bit more work. So VI, as a matter of fact, if we look here between our two potential points, we recognize that VI must be equal to VGS plus V out, or VO, I should say. So why is that? Well, if I just run myself along a KVL loop, let me do it with another color. We'll do green, I suppose. So if I run my KVL loop here, there we are. That's pretty much it. I have that VI must be equal to, or better written probably as 0 is equal to minus VI plus VGS plus V out. Right, and you can almost see that too because the VI is in the opposite direction of V out, okay? So it makes sense that you have a minus sign here. If you follow, another way to look at this is, those of you that are struggling with it, let's go ahead and erase all this. So another way to see this is if you look at the plus minus signs moving around the circuit, this is the one that's backwards. Okay? Put my dots back in here real quick. Sorry, still getting used to teaching with a pen. I'm used to chalk, actually. When I used to teach math, I would always teach on a chalkboard. I never even used whiteboards, so this is all kind of new. But I like it. It's nicer. And it's not as messy as the markers, so we're good. Okay, so we have VI is equal to VGS, and now we're going to redefine V out. Well, we already know what V out is equal to, right? We found it over here. So we're just going to plug it in right down here. And that's just GM, VGS, RO, RSS, RL, and then from here, you can see that this has VGS in common. So VI is actually just equal to VGS for 1 plus GM, RO, RSS, RL. And now we can put the two sides together. This will be our peanut butter side. So V out over V in. This will be our jelly side. And what we end up with is the VGSs are going to cancel, and we're left with just GM times RO, RSS, RL over 1 plus GM, the same, RO, RSS, and RL down to the denominator. So it doesn't take a math wizard to tell you that this is always going to be basically less than 1 for any reasonable values, because up here we have some value and down here we have that same value but always plus 1. So no matter what, this is going to be just below 1, or closer to 0 depending on how small this gets, or 0 over 1. So anyways, that's it. We actually have this defined as AVI is essentially always less than 1. And more explicitly, we can calculate it this way. Calculating RIS is actually pretty easy. All we got to do is look at our IN. So IN is coming in this way by convention. So II. Then we have VI between our two nodes here and here, two input terminals. And we just watch the current flow. So it's going to go through here, come down, and through here in parallel. So effectively we have a voltage drop of VI, right? And that's equal to our current, II, over R1 in parallel with R2. So in the end, we're just left with RIS equal to V out over V in over IN by definition. So that's just equal to R1 in parallel with R2. So pretty straightforward. I'm not going to belabor this too long. Now we're going to do the common drain calculation. The common drain RO calculation. And for this, we're going to reintroduce the IX VX notation that you've probably used before when solving Thevenin equivalence. And in this case, we're looking for a resistance value with Thevenin equivalence. So first step in this is recognizing that RO is equal to V out over I out, which is fine. But we're actually going to use a substitute here. We're going to use VX over IX. And our VX and IX are defined here and here. Again, this is pretty common technique. You should probably be familiar with this. But just so you can kind of track along with what's going on here, we have this current that's coming in, and it's getting split between little RO and RSS. And we also have this guy here that we see. So RO sees little RO and, big RO sees RSS and little RO, and that current source, which has a value GM VGS. Okay. So effectively, we have the following: IX coming in plus GM VGS coming in. This is a little VGS. Must be equal to whatever's going through RO and RSS, right? And the voltage potential here we defined arbitrarily as Vx. Okay? And again, we're evaluating this guy when Vi is equal to 0. So this whole part of the circuit we don't really care too much about. Note here that just because Vi is equal to 0 does not imply VGS equal to 0. This is not true in this circumstance. Recall that from before we had VGS was between here and our grounding source. In this circumstance, it's not. It's actually between here and here. Still between gate and source, obviously, but it's not going down to the ground anymore. So when we do this VI, between VI would live right over here, between here and here. This is where VI lives. When we make VI equal to 0, it's not the same as the potential between here and here anymore. So hopefully you recognize that. Okay, then we'll go and draw this other one just for funsies. Now, all we do from here is a little bit of algebra. We isolate IX. And we go ahead and pull Vx out from the expression, noting here that as a matter of fact, when we push this GM VGS over to the other side, it has a minus sign associated with it. But if you see here, this guy is going in the opposite direction. Our VGS effectively, since this is now swung down, right? We've taken this whole part of the circuit out, and so now the gate, you can think about it as swinging down here and now being attached basically right here for this equivalency. So VI has done something very funky where now our VGS goes minus plus VGS here. And here's the rest of our diagram. GM, VGS. And I'm not going to draw this all out. It's just etc. So now VGS is minus plus top to bottom, where Vx is the same potential bottom top, right? So effectively, we can exchange Vx is equal to minus VGS, which is very convenient for us, because now what we can do is we have 1 over RO plus 1 over RSS plus GM. We subtracted it from both sides, but there's a minus sign associated with converting it into VX. X, converting that VGS into VX. Okay, so from here what we can do is we say, all right, just divide and swap over to the other side. So now RO must be equal to 1 over all of this stuff, which is just as we know. So let's write this a little bit more formally, IX, which is equal to all of these guys in parallel. RSS, okay. Come on, pen. RSS in parallel with 1 over GM. This seems a little odd until you think about what GM actually represents. It's transconductance, right? It's conductance. What's 1 over conductance? Well, it's a impedance or resistance. So this makes perfect sense. And this is a nice way to incorporate our GM here. And as we'll see, this inclusion is actually really important for us in sort of defining the parameters of our different amplifier configurations. So there you have it. This one's a little bit more complicated to do, but it's not too bad once you see that the VGS here can swing down. That's really the big kicker to meet up with your Thevenin equivalents. Okay, let's see here. Okay, let's discuss the common gate amplifier now. So note here that we're starting off with that same bias circuit, and it's isolated by all these capacitors. We're assuming still that those are friendly to our frequency. And a lot of stuff different for this one, but notice our gate is tied to ground as promised, hence common gate. And our out this time is on top by our drain. And our VN lives here. So V out is up top, VN is up down below. We got our load attached to our out, where our out lives, and we have our VS attached to our VN. So from here, we need to rearrange some furniture so that this circuit makes sense. So typically when you write something out, you want to try to have input, stuff, output, right? We write from left to right. So if we want to do that here, we need to reconfigure our circuit to read from left to right. If you don't, some people's heads will explode, and that's no good. So let's go ahead and do that. So you can see this is just kind of flipped over, almost reflected across that axis, if you want to think about it that way, or rotated around that axis. And then everything's just kind of, your wires are just kind of bent to fit. All right, from here, we have a little bit of work to do to get it to the small signal model. So let's think about what's actually going on here. When we look from our source, we see, here's our source. Let me do it in a color so you can actually follow along. When we look from our source, we're going to see RSS, and then if we come out, we'll see RS. Okay, so we can go towards RSS. It's like a choose your own adventure, right? Or you can go to RSS and go to ground. Let's flip to page 5, and then we run into our... Anybody do those choose your own adventure stories? I love those things. There's some new ones out that I really enjoy too. The old ones are kind of hokey. Anyways, so that comes over, goes to ground. This also goes to ground. Okay. From here, and again, note that our input terminal lives right in there. So from here, let's look from the drain real quick. And from our drain, we see RD and then go to ground. And if we turn and go to ground. If we turn, we can go to our V out, and then after we get past our V out, we get to our load and go to ground as well. But for all intents and purposes, our amplifier lives here. Now from the gate, we just go straight to ground, right? We don't need to go through these guys. This is a shorter, very much shorter path because there's no resistance. So we don't worry about R1 and R2 in our small signal model here. So fortunately, we can cut those out. Now, a lot of you are still screaming at your computer screen, where did little RO go? Well, we don't care about RO in this circumstance. So in the book, we note that in this particular circumstance, it's actually around 1% or less sometimes for the contribution that RO has here. If you were to have it, your small signal model would have it up here. Yikes. That's going to be, this is a big yuck puddle, okay, of stuff to deal with. So we typically omit this. So if you see this on a test or something, I really don't like you guys. And I'm trying to make you fail. So you won't see that from me because I want you to be successful. So the short answer is it really doesn't matter too much in this circumstance because it's not contributing a lot to our model. It's contributing very, very little, and it's a pain in the butt to work with and solve. So for both of those reasons, we omit it, and we assume that lambda is equal to 0. In common gate. Okay? All right, that pretty much builds our common gate amplifier. So let's go ahead and start doing some solving. We got a little bit of funkiness going on with that sitting on top, but I think we can handle it. All right, let's calculate the gain on our common gate amplifier. So AVI is equal to V out over V in, and I'm sure you're sick of seeing this by now, but this is our last one to do here. And as before, we want to think about V out. So initially, you might jump to IO times RL, looking at the current flowing through our load there. This isn't very convenient for us, and so we're actually going to not go that direction. Instead, if we look at what ID is doing with respect to these two resistors, we can easily figure out what's going on. So note here, this is VO, but we have current coming up through our two resistors here, and that current must equal ID. Now here's where the beauty of getting rid of that pesky little RO comes into play. So RO doesn't exist. All right. So we don't have to worry about that. Therefore, we know that ID is just equal to directly GM VGS. So it's very convenient to write this then as minus ID RD in parallel with RL. And then we substitute this in. So we have V out then is equal to minus GM VGS RD in parallel with RL. So this looks pretty familiar to us to a certain extent. And when we divide that out by VI, we're going to know something interesting. So what happens here between VGS? How is it related to VI? Well, VI goes between here and here. And as a matter of fact, because of the way we've drawn this, and you can see this here in the diagram, let's get out our purple pen, because this is important. This is actually gate, source, VGS. But notice the orientation here is minus and plus, whereas in the past, we've seen plus minus, top, bottom. So actually, if you look here, this is just minus the potential of VI. So with that inversion going on there, VGS is actually just equal to minus VI, or if you want to write it the other way, minus VGS is equal to VI. So we can do a substitution real quick here, and V out is equal to not minus GM VGS, but GM VI RD in parallel with RL. This is much easier to work with, because now when I write out my gain equation, the VI cancels, and I'm left with just GM RD in parallel with RL. And I'm done. That's it. So notice here there's no more inverting occurring on my gain, which we'll talk about towards the end here. Okay, let's calculate our input resistance for our common gate amplifier. So notice that we started with this guy up here. And what we're going to do is use a probe voltage source to compute that input resistance. So recall, this is not quite right. We want to actually move this guy. I'm going to move this on the, this should be kind of on the outside. So really our nodes are going to be like here and here for VI. Okay. And what we're going to do is tack in VX and IX. Okay. And those are our test voltage and current coming out. So now we're going to use this calculation for our RIS, our input resistance, because recall RIS is just our resistance here. Right across that line that, I was going to use orange. I promised orange. There we go. So it's right there. So now we go ahead and apply our current here. And our current is going to flow down through RSS. And it's opposed by this guy coming out of here. So we just sum this stuff together using KCL. So we know that V X in this case is just equal to minus VGS, right? Recall our discussion about our sign here. So for our potential, this is going plus here, minus plus. Okay, and if we look at our current flow, we have current coming in here, and it's got to do something over here because we have something pushing against us. So what we have is IX is equal to minus GM VGS, this opposition right here, and then plus whatever is going down through RSS. So we have RSS over, under RSS. So this potential is flowing down through RSS. Okay, but we go ahead and use this exchange, pop that in here, and we end up with IX is equal to minus GM VX plus VX over RSS. And lo and behold, we can factor this out and pop stuff over to the other side. And what we end up with is that RIS, which is equal to VX over IX, is just equal to RSS in parallel with 1 over GM. And recall here that when I made the swap that this should be positive. Apologies there. So that's it. RIS is equal to RSS in parallel with 1 over GM. Not too bad. Okay, we're going to solve our output resistance for the common gate amplifier now. And again, we're just going to pop off our load resistor there and pop in the equivalents, so our little test probe, VX and IX. And from here, it's pretty straightforward. We have a current that's flowing in, this nice IX, and we have it flowing down through here and over through here. And we're evaluating it when VI is equal to 0. So recall RO is equal to VO over IO, which we're going to replace with VX over IX conveniently. And in this circumstance, we're going to look at IX real quick and say, hey, look, IX is equal to that voltage that we built over RD plus the current that's going the other direction, out the other way from this. And that ID is equal to GM VGS. Don't have to worry about that other resistor in here, right? That's nice. But also, we don't have to worry about VGS at all. Why? Well, because of this condition. And we're not dealing with the common drain amplifier anymore, so we have this nice dichotomy between top and bottom again. That's convenient for us, because now VGS is going to be equal to 0 when VI is equal to 0. Because this potential, although reversed in direction, is still equal to 0. So this is equal to it's equal to VGS. So this whole thing goes to 0, and therefore Vx over Ix is equal to Rd, which should look mighty familiar to y'all. So that's it, and this is typically going to be on the order of 1 kilo ohm. Okay, so now I'd like to take a minute to make a big table of everything we've learned so far and our different values for things, so that we have them conveniently in one place, and so that we can compare everything together. So our common source typically on the order of -10 to -30. Remember, that's unitless. So this is relatively large, and it is inverting, meaning that we have a 180-degree phase shift, because recall that a negative sign in AC land is just a phase shift, or a shifting of whatever signal we have in there, waveform. Okay, there's that. And our input resistance is relatively high. It's on the order of 100 kilo ohms. It's relatively large. Output resistance is on the order of like 1 kilo ohm. So we say it's moderate. Okay, and overall, we have a big gain, a voltage gain, and it's inverted. Looking at the, I don't have much room for my equations in here. I'll do the equations on the next slide. Looking at the next part, we have CD. This is typically what we call an opener stage to multi-amp systems, and it has big power gain, right? Because of the big current gain, because it's sourcing current. So you'll typically see this one, and then depending on the situation, you'll see a common source or a common gate attached to that. Our voltage gain is relatively low, so it's usually less than 1. Let's say it's small, it's non-inverting. And another way to say that is it's attenuating, if you wanted to think about it that way. And it's our input resistance is on the order of around 100 kilo ohms, so it's relatively large in that respect. And then it's small for our where did we go? Oh, that's why. And it's small for our output resistance, around 100 ohms. Okay, so no big deal there. In this one, 1 over GM is dominating. Okay, and it arises from looking at the source. For CG, we have big gain again. And big voltage gain. And this time it's non-inverting. And it's with a low input resistance. That's a big difference here between the CS and the CG. So about 10 to positive 30 on the gain. We say it's large. And we're on the order of 100 ohms resistance for our RIS, our input resistance. So that's small, as we said. And our output is resistance is moderate, on the order of 1 kilo ohm. And again, this input resistance is driven also by that 1 over GM, 1 over our transconductance factor, which is the biggest driver we have there for making that happen. And that's pretty much it. Let me go ahead and do the next slide as all the tables. Okay, so here's all of our handy-dandy equations. This is for common source. It's for common gate. And this is, oops, this should be common drain. Excuse me. And this one's common gate. All right, and you can see here our 1 over GM dominating similarly here. So that 1 over GM is really pushing these values here and here down. All right, that should wrap it up for today. I've probably run over time. I apologize. So hope you guys have a happy Monday or whatever day it is, and we'll talk at you later.